Hi, I'm Brian Mahalik from Solar Tech Collective. Welcome to Clamping Down on Solar Hazards, Part 1. In this series, we're going to be talking about why a clamp-on ammeter should be a solar technician's best friend. How to select one, how to use it day in and day out, and what it can do for you both when things are acting normally and when they're not.
Warning, this video is for educational purposes only. Electrical systems contain dangerous voltages that can cause severe injury or death. Installation and maintenance and testing must be performed by qualified persons. Never attempt electrical work without proper training, licensing, and personal protective equipment. Solar Tech Collective assumes no liability for property damage or injury incurred as a result of the information contained in this video.
A clamp-on ammeter can be used to quickly identify potential hazards. It can't identify every single hazard, but using it is a critical standard operating procedure. And it's safe to say that it's a technician's best friend as it's absolutely essential for safety. Checking the wire may prevent a fire. The most important thing to know about solar modules is that if they're exposed to sunlight, they can produce voltage and current, which is a wondrous thing, right? They just want to produce energy. But this can be a bit of a challenge if we want them to stop producing voltage and current, as it's real hard to shut off the sun. And this can be a problem because PV systems have many non-load break rated devices. These are devices that are not intended to be opened or operated while there's current flowing. Some examples include plug connectors, fuse holders, and bolted terminations. Both abnormal and normal current flow can cause issues with these devices if they're not handled properly. If a device is non-load break rated, like this mating connector here, it's going to be marked "Do Not Disconnect Under Load" or something similar. And the purpose of that marking is to let us know that we shouldn't open it while there's current flowing unless we want to let the sun out. In case you were wondering, this is what that looks like. And once more for good measure. This is what those connectors look like afterwards. You can see that there was significant damage, but the worst damage isn't visible because it happened to the current carrying parts inside. If we were to reuse these connectors, they'll have a high resistance connection that'll eventually fail, perhaps spectacularly. But this isn't the worst that could happen. It could lead to a fire or potentially harm someone on site. Touch-safe fuse holders like those in this combiner box are also not designed to be opened under load. And there's a whole lot more sunshine to let out in a combiner box. Let's talk about how to safely use our clamp-on ammeter to verify a lack of current and keep the sun where it belongs.
Well, verifying correct meter operation is absolutely critical when we're testing a circuit to make sure it doesn't have any current on it. There's a lot of ways to get a false zero reading that can make you think things are okay when they're not, and that can lead to hazards. Meters fail, batteries drain, meters are set wrong. All of these can give you that false zero reading. So we want to go ahead and measure an operating circuit to verify that the meter can actually read current before we try and use it to make sure that there isn't any current. That could be testing the circuit before we shut it off and then retesting it when it is off to make sure there's no current. Or it could be testing a circuit on an adjacent system, maybe another inverter on site that's still operating if we've already turned our target circuit off. Let's go ahead and take a look at a video from the field of verifying correct meter operation before testing for a lack of current on a circuit.
Before we do any testing on the inverter that we're troubleshooting that has the issue, let's verify that our meter is operating correctly by testing current on an inverter that is operating at this very moment. First step, let's zero out our multimeter. Cut. Let's talk about zeroing out our multimeter real quick. When a clamp-on ammeter is attempting to measure alternating current, it's looking for the unique electromagnetic field that AC creates. So there's no need to zero it out. When it's attempting to measure direct current, it's picking up all of the static electromagnetic fields in the environment. We need to zero it out to tell it to ignore those and only pick up what's coming from the wire. We want to zero it out when it's in the position that we're going to use it in and when it's near the wire that we're going to be measuring. We're zeroed out. Let's head back to the field. All right, so we've got 5.8 amps there. 6 amps. Strings are relatively consistent. Meter's working well. So let's move back to our inverter that has an issue and start testing there to make sure that we have no current present before we disconnect anything.
Now that you know your meter's working correctly, what do you do next? Well, before you open any connector or fuse holder on a site, you have to check every single circuit for current. You always want to make sure there's no current flowing before you open a connector or a fuse holder. You don't want to let that arc out. That can start a fire. First, you need to zero out your meter. Make sure that you're getting an accurate reading from your meter. You should be aware that the current value is unlikely to read as actually zero. We'll usually see some fluctuating low current values when we check PV circuits. Less than about a half an amp is nothing to be worried about. Okay, let's head out into the field and watch this in action.
So having a clamp-on ammeter, but most importantly, knowing how to use it properly, is essential to safely and effectively working on PV systems. But how do we know that we've got the right tool for the job? When choosing a clamp-on ammeter for a specific task, the place to start is with the current type and range. Not all clamp-on ammeters are able to measure direct current, so make sure that whatever meter you're using is able to measure what you're looking to measure. The range for a multimeter is the minimum and maximum values that it can safely measure for a given setting. For current, it might be able to measure up to 400, 600, or 1000 amps, but the most important thing here is that its maximum value is greater than the maximum anticipated circuit current. Using the wrong range, for example selecting a meter that can only measure up to 400 amps, and trying to measure the current on a circuit that's carrying 650 amps can lead to false zeros and/or incorrect results. So why don't we just use meters with a high range all the time? Well, if we try and use a meter with a high range on a circuit with low current, the results aren't going to be that accurate. For example, a meter with a range up to 1000 amps isn't going to be the best tool for measuring current on a 15 amp circuit.
There's another rating you need to be aware of for your meter, and that is the category rating, category 1 through 4, which is a measure of the meter's ability to withstand transient overvoltage. What that really means is that if there's an abnormal situation, a voltage surge, maybe from a lightning strike, that is the ability of the meter to withstand that overvoltage, meaning it's not going to explode in your hands. The CAT rating of the meter protects you, the user. For PV circuit measurements, we need to have a CAT 3 or higher rated meter. There is an IEC standard 61730-1, which defines PV circuits as category 3 for these purposes. They are distribution or fixed installation conductors. Category 4 applies to things like utility and service entrance conductors. If you have a CAT 4 rated meter, that's a higher rating, it has a higher withstand value, that's perfectly acceptable to use, but you shouldn't be using a CAT 1 or 2 rated meter to measure PV circuits. And just to mention, this is different than the voltage range rating of your meter. It is a separate rating on the meter, and it is not directly correlated with the voltage range.
Two other key characteristics to consider when selecting a clamp-on ammeter are resolution and accuracy. Resolution is the smallest incremental value that the meter can display. Basically, how many decimal points of data do you get? Tenths of an amp, hundredths of an amp, thousandths of an amp? It may matter, especially when you're testing lower current circuits. Higher resolution may give you some benefits in terms of determining if things are working correctly or not. It also ties back into range that we talked about earlier. Some meters will have a dual range function. Maybe it can read up to 1000 amps and you only get tenths of an amp increments. Whereas if you set it to a lower range, 40 or 60 amps, maybe you get hundreds or thousandths of an amp increments at that lower range setting. Accuracy is the maximum difference between what the meter says and what the real value is. Higher quality meters are going to be more accurate. Meters can drift. They may need to be calibrated. We'll follow the manufacturer's instructions for that. And different manufacturers are going to give you these values in different ways, which can make it difficult sometimes to truly compare. What we'd really like would just be a percentage. Is it 2%, 5% accurate, whatever that number may be? Again, a higher quality meter is going to give you better values. You also see that at wider ranges, often the accuracy is going to be less than if we have a lower range. And also, our accuracy will change based on how the clamp is placed around the wires themselves. If you're out on the outer edge, it's going to be a little less accurate. If you're right dead center through the middle of that clamp, it's going to be more accurate. Does it really matter for what you're doing? Probably not. Probably not. We're always going to have some fluctuations when we're doing our clamp-ons anyway in terms of the current value we read.
Let's look at some common clamp-on meter current and voltage ratings. These will always be marked on the case of the meter itself. It's going to vary exactly where, but if you look, you'll find them. You can see that there's quite a bit of variation for the Cat 3 and Cat 4 voltage ratings, as well as in the maximum amount of current that they can measure. You end up paying for those higher voltage and current ratings. So if you're selecting a meter, you're going to want to choose a meter that's appropriate to the type of work that you're doing.
PPE, personal protective equipment, is your last line of defense when things go wrong. Don't forget your PPE. PPE is site-specific. It depends on the hazards that are present at a particular site. For example, arc flash and shock hazards are going to be very particular to the level of energy that's present in a combiner box or an inverter cabinet or an AC panel board. And there should be labeling on all of this equipment. There are requirements for labeling so that you know the proper PPE to wear for working within the arc flash boundary and within the restricted approach boundary for shock hazards. You can see in the image on the screen, arc flash face shield, FR clothing, insulated gloves. All of that is appropriate based on the calculations done for this piece of equipment, which are site specific. What other hazards exist on a site? Do you need earplugs? Is there a lot of construction noise? Do you need steel-toed boots? It's critical that you have the right PPE and that you know how to use it so that you can stay safe on sites. And last but not least, don't forget your electrically rated, typically a Class C fire extinguisher. You need to have it with you no matter what type of site you're working on, and you need to know how to use it.
Thanks for watching. There are 2 other videos in this series. Click to check them out and subscribe for the latest on electrotech.